It's 1 o'clock, so let's get started. Today is one of my favorite lectures and maybe one of the most important lectures in the course. We're going to talk about gradient descent. So we've already talked about optimization at a high level. What does it mean? And we've thought of a lot of the methods in this course as optimization problems. And today we're going to talk about one particular algorithm for actually solving optimization problems. So a rough outline for today is we're going to talk about why do we actually need gradient descent. We saw the normal equations last time for linear regression. Why can't we just do that for everything? And we're going to talk about some of the parameters of this algorithm, like the step size. We'll talk about implementation and this thing at the end that I call data space versus parameter space. So a couple of motivations for today's lecture. One motivation is that we talked about the complexity last time of the normal equations, which was forming this matrix x transpose x and then solving a d by d linear system, which gives us this cubic time complexity in d. And what if we have a huge problem, say with a huge number of features, and we just can't deal with this? What do we do? And gradient descent will give us one alternative that may, in some cases, be better for very large d. Another motivation is, what if we want to change the fit, the linear fit that we get? So we went with the squared error loss function the last two classes because I claimed it was reasonable, it was easy to minimize. But the squared error loss function can sometimes do crazy things. So, for example, and you don't need to look at the code too carefully right now, but if I generate a synthetic data set in one dimension with these couple of outliers, then you can see that the line gets really pulled by those outliers, and it's exactly because we're taking the squared error. So any kind of big distance between the line and a point, that gets squared when we compute how upset we are by it, because that's what the loss function really tells us. And so might we want to do a linear regression with a different loss function? Okay, but the normal equations were this nice, beautiful thing that we derived last time. We took the gradient, set it to 0. It all worked out beautifully. We got this linear system. But that isn't going to always work out. And so if we want to change the loss function, can we come up with a general purpose optimization algorithm for minimizing whatever loss function? And not truly any, but a large and interesting class of loss functions that will do things like solve this issue. So any questions on the motivation? Okay. For those of you who haven't seen this before, it might be a bit shocking what a couple of outliers can do. Okay. So enter gradient descent. Gradient descent is an optimization method that works as follows. We start with some initial guess for our parameters w. And then we say, what is the gradient of the loss with respect to w? So what we did last time, we calculated that same gradient. We just set it to 0 and solved, and it was all nice. But if it's not so easy to solve that equation, we can take the gradient and consider its interpretation, which is it is the direction of steepest increase of the function. And therefore, the negative gradient gives us the direction of steepest decrease of the function. So the intuition of gradient descent is I'm here. I have a direction where things are supposed to get better. if I move W in that direction, my loss should go down, which is good. I'm trying to minimize the loss. So let me move myself in that direction by some amount. And then I'll be in a new place, and I can compute the gradient again, and it'll give me a direction, and I can move in that direction by some amount. And if I keep doing this, hopefully, I will actually converge to the minimum. So that's the basic idea. And, oh dear, let me deal with this. And the notation we're going to use is we'll use superscript for iteration t. And sometimes we also use lowercase t to mean the number of test examples in a test set, so you should just pick that up from context. So we're saying we start from some initial w, and we've already reserved subscripting for indexing into a vector, so that's why we're superscripting. The next w, wt plus 1, is the current w, wt, plus some alpha t, which we can call the learning rate, multiplied by the gradient. So alpha here is a scalar, and the gradient is a vector. The dimensions of the gradient are the same as the dimensions of w, so that makes sense. And we're moving ourselves in that direction, and the minus is because we're minimizing or trying to decrease the loss. And if we were maximizing, we would have gradient ascent, and we'd have a plus sign. So there's a bunch of text on this slide. A couple more things to say about it is that we have to think about how to pick the step size. The gradient is a local property. It just says right here, this is the slopiness of the function in various directions. And so if I take a tiny step, then everything's going to be fine. If things are getting better in this direction, I take a tiny step in this direction, meaning sufficiently small alpha, I should be okay. But if I take a giant step alpha, then all bets are off. In fact, maybe my loss will even go up if I take too big of a step, because I've just gone way somewhere different. And the gradient is not telling me about something way far away, it's just telling me about a very local property. Raga?
No.
Oh, okay. So gradient descent converges to a global optimum if f is convex. And we've been talking about convexity, and now we start to see why we care about convexity. It's this property. If we can show it for a particular loss function, like we showed it for the squared error with linear regression, then we can fairly confidently apply this and eventually get to the minimum. And there's also this issue of specifying the initial guess, and let's just say we initialize randomly. For now, since our function is convex, it shouldn't matter that much where we start. We're all being pushed down towards the minimum. If we start closer to the minimum, we will probably get there faster. But we're probably not going to mess everything up if we pick a bad guess, because we're dealing with these nice convex functions. Any questions about this or about this equation on the slide that's pretty central to the lecture? Okay. So I just wanted to point out that there are different conventions about how to write down gradient descent, and the way we've written it is alpha times this gradient vector. And I just wanted to point out that the gradient vector is not just a direction, but it also has a magnitude. And so the size of the step I take, at least the way we've written gradient descent, is not alpha. It's actually alpha times the magnitude of the gradient. And so if I tell you, let's use a constant alpha, that might worry you at first, because I kind of imagine myself taking smaller and smaller steps as I approach a minimum. If my step size stays constant, how am I ever going to exactly land on the minimum? I kind of want to approach the minimum. And the answer is, the way we've written it, we're trying to find a minimum, which is the same as saying we're trying to find a place where the gradient is 0. So that gradient term, its magnitude should also be going down as we get where we're going. Because in fact, where we're going is the magnitude of the gradient is 0. And so that's why having alpha to be constant is not totally insane. Name?
Matthew?
Matthew.
Are we worried all about cases where you kind of hop back and forth?
Are we worried about cases where you hop back and forth? So let me draw a picture. So imagine just a one-dimensional optimization problem. So we just need to move left or right. We're trying to get here. Say we start here. You could take little steps and sort of go along and eventually approach. So this is what you meant by back and forth, right? Crossing over the minimum.
Yes, but you never actually go down, though, like if the slope matches up.
So there's two hopping situations. There's hopping like this, which isn't that horrible. But there's also hopping where your step size is so large that the loss is actually higher at the next iteration than at the previous iteration, and that's what I was describing earlier. The gradient is just a local property. So yes, if alpha is too big, you may take steps that actually increase the loss, and the more iterations you run, the worse things are going to get, and eventually you'll just get not a number or whatever. But this thing I described here, it's not necessarily horrible. If you're making good progress towards the minimum, that's good. Yeah, Bianca.
What if you have a very flat curve?
What if you have a very flat curve?
Yeah, it goes like this, and then runs for a really long time, and then.
So
it dips really low really quickly if you have a large learning rate, but then, or if you have a really small learning rate.
Yeah, so the question is, what if you have a really flat curve, then maybe it's going to be hard to reach the minimum. So I'll say a couple general things about that. Yes, some functions are going to be easier to minimize than others, and how your particular implementation responds to that function depends on the details of what you do. So how am I picking alpha? I said alpha could be constant. There are many other ways to pick alpha, some more clever than others, that might better deal with those kinds of situations. So that is a problem, but it's also not hopeless. Okay. I'm not going to say too much about other methods of picking alpha for the moment. Except to say that the code provided for assignment 3 comes with a function called findmin, which is essentially gradient descent using a more clever way to pick alpha that's adaptive. And you're not responsible for digging into that, but you are welcome to dig into that if you're interested. Okay, and then just to revisit this issue of when do I stop. This is a numerical algorithm, right? So you're probably not going to reach a situation where the gradient is literally 0. You might get yourself to machine precision, but maybe you don't actually care about getting the solution to machine precision. So one common strategy is to pick a tolerance that says if the magnitude of the gradient is less than some small value, then I'm happy. Because remember, the magnitude of the gradient being 0 is the solution. So in other situations, you might specify some number of iterations and just say, we talked about this a little bit before. Each iteration takes an hour. I only have 10 hours, so I'm just going to run 10 iterations. And if you do that, you may want to check how big your gradient is when you're done to have some sense of how did you do, but such situations could arise. For the type of things we'll be doing in this course where it's not taking hours, we can just specify some tolerance and optimize up to that tolerance. Okay. So we can compare good old least squares doing it the way we talked about last time or doing it the way we talked about today. And we figured out the computational complexity of the normal equations last time. With gradient descent, the computational complexity is a little more hazy. We can figure out how much it costs per iteration, which is computing the gradient. So we essentially have to do a matrix multiplication that's going to cost us O of n times d. But then I've written there n dt, so we have some number of iterations t. And we don't exactly know in advance how many iterations we need to do, so it's a bit harder to say the computational complexity is blah. In this course, we don't really go into any optimization theory proving rates of convergence or how many iterations would I expect to need to reach a certain tolerance. There's other courses that will go into that more, like Computer Science 406 and 540. So if you're interested in learning more about that, I suggest checking out those courses. A couple other notes here is that all these things are just big O, so we still don't have the constants. It's hard to say this is definitely going to be faster than that. There's a lot of implementation dependence. When you're solving a linear system, you're using some super optimized linear algebra libraries written in Fortran or something. If you just implement gradient descent yourself naively, maybe you did it really well, maybe you didn't. So it's hard to know how long it's going to take. But just a note that we can kind of assume the number of iterations does not depend on d, and that gives us hope that maybe for very large problems this might be the way to go, or if not this, there's one other optimization algorithm we cover in this course, which is stochastic gradient, and that might be the way to go as well. Fed.
So forming X transpose X says it's O of ND squared, but below you are also using it. Why is it only O of ND?
Great question. So Fed says, how can I claim that multiplying, how can I claim that I can do this in O of ND if forming X transpose X costs me ND squared? And the answer is I can do it in this order. And then I'm doing a matrix vector product and another matrix vector product. Okay. Let's look at some code. So first thing I'm going to do is just generate a bunch of random numbers, 10 dimensions, 1,000 points. You can, again, play around with this as much as you want. So I'm going to compare 3 different approaches to linear regression, just vanilla linear regression like we talked about it. And the first one is I'm going to call the scikit-learn function linear regression. I'm going to fit it on the data, and then I'm going to print out LR.intercept, which is what we were calling beta, the intercept term, and LR.coef, which is what we've been calling W, the regression coefficients or parameters. And I get some values that it's okay if they don't mean anything to you. They don't mean anything to me either, but I want to see if they're the same as the ones I get using other approaches. So here, last time we talked about the normal equations. And here they are. So this line that I've highlighted was the punch line from last class. It was x transpose x w equals x transpose y. We need to solve that linear system, and you can solve using whatever solver. I'm using the NumPy solver. Pass in x transpose x, pass in x transpose y. And the only difference is that I mentioned with the intercept, one way of dealing with it is to add this column of 1s into x. And that's what this line above is doing. I'm just making a matrix, or a vector of 1s of length n, and then I'm appending it to x. Okay, so we can run this. I'm pretty zoomed in, but okay, they both fit. So that's good news. We get the same thing, and I'm not very surprised. I would expect scikit-learn to basically be doing the same thing, but wrapped in a lot more fancy stuff for different options and all kinds of nice extra things. But roughly, it's probably doing the same line. Okay, fine, great. Here's my gradient descent implementation. I pick some alpha. In this case, I'll just use a constant alpha, and I'll make it small so I don't have to worry too much. And I'll define a function for the gradient. I create an initial guess W, which is, in this case, all zeros. And then I say while the norm of the gradient is greater than some value. So once the norm of the gradient is smaller than 0.001, I consider it close enough to 0 that I'm happy, at least for the purposes of this demo. And then it's just this one line. And if you prefer, maybe this is even more explicit. It's the same thing. Just exactly what we had earlier. New W equals old W plus a step in the negative gradient direction. I didn't run the upper cell. Okay, guess I need to zoom out temporarily. Okay, so we can see we get roughly the same thing, not to all the digits. For one thing, I didn't ask it for that much precision, but this is reassuring. And you can play around with this. You can change the initial W. You can change alpha. I'd encourage you to do so. Fed.
The add operator is that matrix multiplication?
The add operator is matrix multiplication, which I thought all of Python 3 had. I recently learned only Python 3.5 and up has, but probably most people are running Python 3.5 or 3.6. This is good. We can optimize things now with just a loop and one line of code, really. And I haven't gone through all the formal assumptions. The function needs to satisfy this to converge, et cetera, et cetera. As I said, that's beyond the scope of this course. But for our purposes here, this is good. Okay. So now I promised you at the beginning that we were going to talk about robust regression, so let's do that. So let's try this objective. I tried to convince you earlier that the whole problem with the squared error is that big distances became huge distances when you squared them. So the absolute value error seems reasonable. It says if something's big, fine, that's not that great, but I'm not going to square it. But now we have no normal equations. So one way we can approach this objective is gradient descent. Except there's this issue that the function is non-smooth. So we have this point in the middle of the absolute value. And I sort of said we wouldn't go into the nitty-gritty of the assumptions that made gradient descent work, but one of them is smoothness. So I'm just going to do this in one particular way that I think will be easiest for us to look at. And then I'll talk later about the general approach that we're going to follow in this course to deal with this smoothness issue. Okay, so here's a random data set. Let's pick an even worse one. That's nice. Okay. So this is least squares. And let's actually derive the thing in one dimension for the absolute value loss. So our loss looks like this, just one dimension for our demo. So W is just a scalar. Beta is our intercept term. I'm writing f of W and beta because those are the two parameters we're learning. So Wx, sorry. Wx plus beta is our prediction, minus yi is the true value, absolute value, sum it up. So if we want to take the gradient of this, we just need the two partial derivatives with respect to our two parameters, w and beta. And we can apply the chain rule the same way as we did before. And first we need the derivative of the absolute value function. Looks like this. So how do I do this from your point of view? So from your point of view, this is positive x, right? And this is negative x? Okay. So the derivative of x is 1. Derivative of negative x is minus 1. So we can just conveniently write that as this sign function that I've written there, which looks at the number and spits out the sign. Is it positive or negative? So positive numbers, derivative is plus 1. Negative numbers, the derivative is minus 1. And other than that, it's just business as usual applying the chain rule. So when I take the derivative with respect to w, the x comes out. When I take the derivative with respect to beta, the inside derivative is just 1, so I don't need to do anything. Okay, now I'm really just turning those two equations into code. If you look at those two derivatives and you look at those two lines of code near the bottom of the screen, sorry, it's really just a one-to-one correspondence between those equations and the code. And let's not get too much into, for the moment, this thing I'm doing with the step size, because this is not the approach I'm going to take in this course. I just wanted to do it simpler first for the demo. Okay. Are you ready? So this is, for me, an amazing moment because we had a problem which was our outliers messed up our line. And again, we talked about outliers. All the usual warnings apply. Maybe they were not mistakes. Maybe they were real things and we want to model them, but we're assuming for today they were garbage points that we didn't want to model. And they were totally pulling the line way out of whack from the non-outliers, and then we just thought about it. We said, why is this thing getting messed up? Maybe it's getting messed up because I'm squaring something. And squaring something is a huge penalty for big mistakes. How about I do this other thing? Okay, we'll do the other thing, but now we can't use the normal equation, so we'll do this gradient thing. And it just kind of works, which is quite nice. It's really from thinking about it all the way to doing it. Yeah, I forget your name.
Jeannie.
Judy?
Jeannie.
Jeannie.
Was this similar to the assignment where you have k-medians and k-means and how k-means kind of work?
Is this similar to the assignment with k-medians and k-means? Yes, there's actually a very deep connection here, which is that the mean of a bunch of numbers is the thing that minimizes the squared difference between it and all the numbers. So if you give me 10 numbers and then say, pick something W that minimizes the squared distances, that thing will end up being the mean. And if you say pick the thing that minimizes the absolute value distances, that thing will end up being the median. So it's not even kind of similar, it's actually very, very related to this. We're doing a median flavored thing here with the absolute value loss. So the intuition that applies for median being robust applies to this being robust. And if we have time, which we probably won't, then we can talk about it a lot more. Otherwise, we can do it next time. Okay. So I had a... You guys are very patient. I had an issue last year that I gave this lecture and a huge portion of the class came out of it thinking, oh, gradient descent is this thing we use for robust regression. No. Gradient descent is a general purpose optimization algorithm. You give me a function, if it's convex, you do this and you'll get the minimum. And that might not even have anything to do with machine learning. You can just optimize stuff. We're using it for machine learning, and in particular, we just used it for robust regression. And the other problem I had last year is people said, there was a question on the exam, why are we using gradient descent? And a ton of people said, because there's a non-differentiable point in the loss. No. In fact, it's the other way around. We're using gradient descent despite the non-differentiable point screwing it up, and we have to be careful about that non-differentiable point. But we're using it because in almost all cases, there's no beautiful normal equations. We just have some loss, and we need to deal with it somehow. We need to solve an optimization problem, and this is a method for solving optimization problems, and the one that we teach in this course. Ali.
About the mean and median thing, like k-means versus k-medians. So we were wondering, wouldn't the mean minimize the absolute value distances?
Wouldn't the mean minimize the absolute value distances? No. The mean minimizes the squared distances. And in fact, on the k-means assignment, when you were plotting, you had to add that error function, and you implemented it, and it was the squared error. There was also no coincidence there.
Okay.
You were actually plotting the loss that k-means was minimizing. And then likewise for k-medians.
Right.
But we didn't spend enough time on that to really deal with it, so if you want to ask on Piazza, we can start a discussion.
Thanks.
Okie dokie. So we can make all kinds of modifications now. Instead of robust regression, we can do brittle regression, meaning we can pick some loss that gets very upset when I make a mistake. And now it's going to extra accommodate outliers, even more than least squares, if that's what we want. because maybe all the points are valid and we just don't want the biggest error to be that big. Okay, come up with some loss that reflects that, minimize it. And it's not just for linear models, right? Whatever model, if you can write it down as a loss, and especially if it's convex, you can minimize it. Okay. I have to add this slide in to not upset certain people in the department, because there's this thing going on where gradient descent, as far as optimization algorithms go, is actually very slow to converge, meaning you need a lot of iterations to get there. And yet, it's also used a lot in machine learning and is simple to discuss, which is why we put it in this course. But I just need to say, so that I'm covered, that this is one of many possible optimization algorithms, and certainly not the best one in all situations, or even in the situations that we'll be using it for in the course. Good. Okay, another thing I wanted to say. I'm going to say this many times, but now I'll say it for the first time. I would like you to think about the process as 3 separate pieces. One, what is my model? Linear, for example. I'm doing a linear model, which means no matter what I do after I make that decision, I can only learn functions that are planes or hyperplanes. So if the thing is data are actually curvy, I cannot capture that once I've made decision number 1. I can change the loss. That's decision number 2. The loss will change which plane ends up being the best, given the data set. But I'm still planes, because it's still linear models. So that is a separate decision point. And then the third decision point is, I committed myself to linear models. I committed myself to squared error. How am I going to go about minimizing that squared error? And again, we have choices. Are we going to use gradient descent or normal equations? Normal equations will not usually be one of the options unless we're doing squared error. But am I going to use gradient descent or some other thing? And they're kind of-ish 3 independent steps, but as I said, not quite independent, because your available options at every step may depend on what you decided before. But I saw many students coming out of this course kind of fuzzy between these different steps. And I encourage you to think about things in this way. Fed.
Are pretty much all the models we've learned linear? Or
Are pretty much all the models we've learned linear? No. But it's harder to see that because we, at least within supervised learning, we mostly talked about classification, and it will become clear later in the course what it means to be linear or not linear when dealing with classification. But at the moment, it's kind of meaningless because we're just predicting a category, and it doesn't quite make sense, but it will. So we just started regression, and we've only talked about one case, which is linear regression. On Friday, we'll talk about nonlinear stuff. Okay, this is now my favorite part of my favorite lecture. So listen up. This is the moment here. Very important skill that I want you to leave this course with. I want you to be able to mentally jump between what I call the data space, or the X space, and what I call the W space, or the parameter space, or the model space. A very common issue is people missing that the optimization problem, this gradient descent, is happening in the universe of W. We have some W, we're going to some other W, and however many parameters we have, that's the dimensionality of that space that we're moving around in while we're optimizing. And that's just not the same universe as the data space. So let me put this into a picture. Okay, here is W space. We have two parameters here, W and beta. And we can plot the loss as contours or level sets of the loss, and the star is the minimum. That's where we want to end up. And we could also plot the absolute value loss. And look, it's different, and are the axes the same? The axes are the same. It's different, and the star is in a different place, which is what we were just discussing. If I change the loss, I'm changing my definition of what is better. And so the best thing is now going to be in a different place in parameter space. And so I will end up with a different fit. And each point in this space corresponds to a line in the data space. That's really the punchline. When I'm moving around in W space, I'm optimizing, I'm following the gradient. Wherever I'm at, that corresponds to a line because it's a slope and an intercept, right? I'm moving around in slope and intercept space. And we can look at that. Sorry, too much text. We can look at that. So I pick some initial value, W equals 0, B equals 0. That's this line on the top left, just a flat line. And that is a point in WB space. It's the blue star. You'll see it's at 0, 0. The red star is representing the solution. By the way, where is the red star? It's at W equals something bigger than 0. That makes sense because the line is sloping positively. So I expect the best thing to be a positive W. And now I can run gradient descent. And now I've done a couple of iterations. And the blue thing is moving. That's where I am right now. I'm moving in WB space. I want you to be mostly thinking in model space or parameter space. But don't forget, whenever I take a step, that corresponds to some new line in the data space. And it's kind of interesting to see the evolution of the lines. And eventually, I don't know if I produce enough of these to actually get there. Okay, almost. So you run this for a few more iterations, you'll eventually get there, and that'll correspond to the correct line. So the reason why people get so confused about this is because with linear models, you have one parameter per feature, which means the dimensionality. Notice the left and right side are both appearing on the screen, meaning they're both two-dimensional pictures. It's just a coincidence, and you really should try to appreciate that. It's a coincidence because our linear model has one parameter per feature plus an intercept. So if we have D features, we have D plus 1 parameters. That's what we have here, D equals 1 and the intercept. And yet, our data space is also convenient to plot in D plus 1 dimensions because we have D x-axes, plus we also want to look at the y-axis. And so the thing ends up looking the same in a way that people can get confused in. But we'll talk about models in this course where the number of parameters is not equal to the number of features. And then we couldn't make this kind of visualization. Forget. Tom.
It appears as though you kind of zero in straight towards the minimum.
Yeah.
I remember from yesterday with zigzags. What?
Okay. Tom was here yesterday. Yesterday I was teaching gradient descent in Computer Science 406 because the instructor was away and it was a bit of a different spin on the same topic. So first of all, Tom, the zigzagging came from doing the full-on zigzagging with orthogonality came from us doing exact line search, which we're not doing here.
That's with finding the learning, what we're calling the learning step here, or the learning parameter alpha.
We were picking alpha in a very particular way. However, you could get some zigzagging And I'm a bit afraid to try it, but whatever. Let's make alpha bigger. Yeah, so see here it's too big, and we're actually not converging. But if I had all the time in the world, which I don't, I could find you an alpha that wasn't too big, so it did converge. But it didn't just make a nice, pretty curve, but it may dance around a little bit, but still get there. And that's exactly just the two-dimensional version of this discussion. Okay, obviously I would not ever try to go through that big thing of text in a lecture, but it was just something that I wrote up as a Piazza answer last year, and it seemed valuable, so I just put it there so that you have it, and I recommend to look over it, and I'd be happy to start a Piazza discussion this year. But it really goes into the details of why the absolute value thing gives you robust regression and why it looks so perfect. It's not even kind of near most of the points and ignoring the outliers, but it's right on the points. And that's not a coincidence. You can really think through why that happens. Or in other words, why it would be unfavorable to move a little bit away from right on the bulk of the points, and you can read about that later. Ari.
So robust here, you just mean like ignoring outliers, not sensitive to outliers?
Correct. By robust, I mean not sensitive to outliers, with the disclaimer coming later that we're only talking about outliers in Y, really. But you could absolutely have outliers in X, and we just don't get to that in this course, but we do get to that in 540. Okay, so for later, so much stuff, so little time. Okay, I have to just say this very quickly, and we can come back to it next time. The way we deal with non-smooth loss functions in this course is to pick a function that has the same properties we desire, but is smooth. And skipping over all the words for a minute, the red thing solves our problem because it grows linearly when you get far away, meaning big penalties don't get squared, they just penalize you linearly. But we just smoothed out the part we were unhappy about and matched them up nicely so that it was differentiable everywhere. And this particular function is called the Huber function. There are many ways of smoothing out the absolute value, and you'll explore a different one on assignment 3. So we will need to return to this on Friday. But briefly, I did the math, I ran the code, and just wanted to say it still works pretty much the same as the absolute value because you might not care that much what's going on around 0. The whole point of the robustness was what's going on far away. I knew it. We'll have to come back to that. We'll come back to that on Friday. It's fine. So let me summarize before you all run away. Today we talked about gradient descent as a general optimization algorithm for finding a stationary point of a function. If the function is convex, that stationary point is going to be what we're after. It's going to be a global minimum. We talked about robust, meaning not sensitive to outliers in Y regression. We used the L1 norm. The general approach, the L1 norm had a little problem. The general approach we'll take in this course to solving the problem is use a similar function that just is smooth but has the properties we want. The particular one we breezed through is called the Huber function. We did not get to the log sum x approximation, but we'll talk about that next class because that's the one that shows up on your assignment. See you then.